Part A. Express 2 over p times p minus 2 in partial fractions. So we'll first write this as a over p plus b over p minus 2. We'll then get a common denominator. So we'll do a times p minus 2 plus b times p. Our common denominator is now the p times p minus 2. And if we compare that to what we started with, we have this. We can now see that the denominator is the same as it would be, as it always will be. So because of that, we can focus just on the numerator. Those two things must be equal to one another. So let's work out the values of a and b that make that happen. So I'm going to let p equal 0 first of all. The reason why I've chosen that is that's going to make this term here become 0 and make it easier for me to work out the a part. So by doing that, the left-hand side is just 2. The right-hand side will be a times 0 minus 2. Like I say, the b term will become 0. So a times minus 2. So that tells me that a must be minus 1. So we can now put that back in the original partial fraction. Right, let's now work out the b term. So this time I'm going to let p be 2. The reason why I've chosen 2 is it's going to make this a term become 0 and allow me to work out the b term. The left-hand side is just 2. And the right-hand side, like I say, the a term has disappeared and I just get b times p. So b times 2. So clearly the b will have to be 1. So now I can put that in my partial fraction. And we're done. We have split that fraction up into its two partial fractions of minus 1 over p plus 1 over p minus 2, which I might just swap around so I don't have the minus at the front. I don't like that minus being there like that. So I think that's a little bit neater to have it that way around. Right, let's move on. A team of biologists is studying a population of a particular species of animal. The population is modelled by the differential equation given there, where p is the population in thousands and t is the time measured in years since the start of the study. Given that p equals 3 when t equals 0, we need to solve this differential equation to show that result there. Right, we're going to separate the variables. So we've got a dp on the left-hand side. So these p terms here, I'm going to move those over to be on the left-hand side. So I'm going to divide by p times p minus 2. So I'd have 1 over p times p minus 2. On the right-hand side, the t terms, let's have a look at that. So I'm going to move this dt over to the right-hand side. So this is going to get multiplied and being over here. So that's going to leave me with a half cos 2t dt. Now, just pause at this moment and have a think. I'm noticing that actually I've got a half here. I could multiply both sides by 2 here and have this on the left-hand side. And I think that's going to make my life a little bit easier, especially considering what I did in part A. So let's actually times on the left-hand side by 2. Not only does that get rid of the fraction, but that means that this is exactly the same as what we did in part A, which means I can replace that. So when you're separating your variables, remember that you can have the constants on either side. I could have left the half there if I wanted to, but hopefully you can see how it makes sense to actually have the half times both sides by 2 and have a 2 on the left-hand side. Right, let's do some integrating. So the first term, the 1 over p minus 2, will integrate to be ln p minus 2. The 1 over p will integrate to be ln p. Cos integrates to be sine, but by the reverse chain rule I need to divide by 2. So it will be a half sine 2t. And not forgetting your constant of integration, which is c. Next, I'm going to work out what my constant of integration is. I'm going to substitute my boundary condition in. So I'm going to substitute 3 and 0. So I'll put 3 here, here, and I'll put 0 here. So ln of 3 minus 2 is 1, minus ln 3. Now sine of 0 is just 0. So the right hand side will just be c. And also ln 1 is just 0 as well. So actually c is just minus ln 3. So I can update my equation. I can say ln p minus 2 minus ln p equals a half sine 2t minus ln 3. Right, I now just need to rearrange this to make it look like this. I just want to make the p the subject. So first, let's use the laws of logarithms to combine these two logarithms together. So it's subtract at the moment, so I'm going to write this as p minus 2 divided by the p. Now I have a single logarithm, so I can do e to the power on both sides. On the left-hand side, the e to the power ln will cancel out and just leave me with the p minus 2 over p. On the right-hand side, I've got e to the power of a half sine 2t minus ln 3. All of that is the power. All of this has to be in the power. But that's fine, because I can do a little bit of simplification with that, in fact. Because I can split those two terms up and rewrite it as e to the power 1 half sine 2t multiplied by e to the power minus ln 3. Which is useful because if I do a little bit of extra work here, if I can remove that minus, then I'll have e to the power ln, which will cancel out. So let's do that. I can remove the minus by moving it up to be a power on the 3. And now the e to the power ln will cancel out and just leave me with 3 to the power minus 1. Three to the power minus 1 is the same thing as 1/3. Right. Next few stages, we're nearly there now. Remember what we're trying to show. We're trying to show that p equals 6 over 3 minus e to the half sine 2t. So the next stage of my calculation, the next stage of my rearranging, I think I'm going to times both sides by 3 just to get rid of that. Just to get rid of that fraction. Just to get rid of this. So if we times both sides by 3, we will get 3p minus 6 over p equals e to the 1/2 sine 2t. Right, all I want to do now is rearrange to make p the subject. So I'm going to multiply both sides by p. I'm going to move all of the p's onto one side of the equation and anything that doesn't onto the other. So let's move that 6 over here and let's move this p to be over there with the 3p. Let's factorise the p outside. So we'll have p 3 minus e to the 1/2 sine 2t. And then let's divide both sides by that 3 minus e to the 1/2 sine 2t. And that's what we needed to show. So that's part B done. Finally, part C. Find the time taken for the population to reach 4,000 for the first time. So we've got our population formula here. We've just shown that's true. If the population equals 4,000, remember that p is in thousands. So that would mean that my p has to be 4. If I say that p equals 4 in this formula, then that's saying that the population is 4,000. So this is the equation we want to solve. So let's multiply both sides by that fraction. Expand the brackets. Let's move the 6 over here and move the 4e to the power on the other side. So the 12 minus the 6 is 6 equals 4e to the power of 1/2 sine 2t. Divide both sides by 4. 6 over 4 is the same thing as 3 over 2. Take logarithms of both sides. So we get ln 3 over 2 is equal to 1/2 sine 2t. Times both sides by 2. Now we can do inverse sine sine inverse of 2 ln 3 over 2 would be equal to 2t. And I don't need to find more than one solution. It just says first time, so I only need to find one solution here, as long as I get a positive value for t, of course. So if I do that, so sine inverse of 2 ln 3 over 2 gives me 0.945, so 2t is 0.94 blah 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 blah, divide by 2 and we get 0.47 Three significant figures, so 0.473. And that's the time taken in years, because t is measured in years, to three significant figures.